everyone, and welcome to part 2 of our lecture on Chapter 2, Understanding and Transforming Raw Scores. So in part 1 of our lecture, we talked about measures of central tendency and data distributions and the way that we can really understand and start to begin to transform raw data. So in this second half of the lecture, we're really going to emphasize the additional ways that we can sort of almost norm or standardize the ways that we transform our raw scores. So to get started, I want to go into a conversation about norms and ranks. So norm referenced assessments involve establishing a standardization sample, which allows us as individual scores to be compared to a sample or norms. So when we have a norm reference group, the standardization sample should be a representation of the intended population. Or if it's not, we're going to have inaccurate comparisons for an individual scores. So when you have norm reference group, you want to get as wide of a sample as possible that you are intended to measure so that you can draw meaningful comparisons across all individuals who take your assessment. But if your assessment has only been standardized with a very small sample of people or a specific type of person, only that type of person should be taking your assessment because that is the only group for which you can meaningfully draw comparisons. Any deviation from that is going to lead you to make inaccurate comparisons. Within norm-based references, we have a couple of different types of references. And one of those is the developmental norms. And developmental norms can be indicated by an individual's grade level, which we call grade equivalence, or by their age group, which we call age comparisons. So grade equivalents are indicated by the grade level followed by a decimal point that represents the 10 months of the school year. So when you have someone who's norm reference and they say that their reading score, they're a 6th grader and their reading score is 9.3, we would say that their grade equivalent is that they are performing at a level that we would expect for a 9th grader in their 3rd month, in the very rare circumstance that a 9th grader in their 3rd month took the same math test as a 6th grader, or at a 6th grade level. So grade equivalence can be a little bit confusing in that a lot of people will make the incorrect indication that if someone performs at a 9.3 grade level and they're in the 6th grade, that means that they're performing at a 9th grade level. That's not necessarily the truth. Again, what I just explained is that if someone in the 6th grade gets a 9.3 as their grade equivalent, they are actually saying that they have obtained a similar score to what researchers would expect for a 9th grader in their 3rd month if that 9th grader took the same 6th grade math test as that 6th grader. So that's where some of the confusion around grade equivalence can come into play, because this is an indicator of whether or not the person that you're measuring or person that you're assessing is performing worse or better than their current grade level. To account for that confusion, we have the second developmental normal age comparison, which is our age comparison, which relates an individual's scores to those of others in the same age group. So how well you are performing in relation to other people your same age. Are you above what we would expect, or are you below what we would expect? And we also have rank, which is an individual's standing within a group. And it may be considered the simplest form of norm-referenced assessment. Furthermore, rank can sort of be a bit misleading because its interpretation is heavily influenced by the size and composition of a standardization sample. So for example, if you say that someone ranks 12th out of 10,000 total people, that means that they're really high up in rank compared to their sample. But if you say that someone ranks 12th out of 20 people, they're in the back half of people. So the size of the group and the type of people that are in the group is going to make a big difference in the meaning of someone's rank. So when we're talking about the composition of a group, if you're saying, well, I ranked 12th out of 10,000 other researchers or other students in Masters of Addiction Counseling programs. That's pretty important. But if you say, I ranked 12th out of the 15 students in just CSU's MAC program, that means something completely different. So, one additional way that we use norms and ranks is the percentile rank. And the percentile rank is used more often than rank by itself because it indicates the percentage of scores that fall below a particular score, irrelative of the size of the sample. So, percentile ranks will tell us, compared to the entire sample, here's how you performed in this sample. You performed at the 50th percentile, at the 75th percentile, at the 99th percentile, whatever it is. It is taking and giving you your rank irrelevant of the size of the group because it's looking at the total sample based on percentages and where you would fall. Percentile ranks are calculated by dividing the number of observations with lower values and score of interest by the total number of observations and then multiplying that by 100. So you're looking at the total number of observations with the low values, then the score of interest for the total number of observations that you're looking at and multiplying that by 100. And you end up with these percentile ranks. And I showed this image to you earlier, but you can see that the percentile ranks fall right here, where you see how people perform based on the number of people in the distribution. One of the limitations of percentile ranks is that the spread of percentiles mirrors that of the normal curve, making the interpretation of percentile changes a little bit difficult, because a greater number of scores fall around the 50th percentile, which means that your median and your mean and your mode are all close together. Most of your scores are going to be close to that. And that's why you see a much tighter display of your percentiles here than you do on the outside or on the tails. So it's more difficult for an individual to move from the 5th percentile to the 10th percentile than it is from the 55th percentile to the 60th percentile. And in order to understand percentile ranks, if they're just said, you have to know that the percentile ranks is based on this normal distribution. And because there are several problems related to using percentiles and other types of scores, many tests make use of standard scores as the most satisfactory method for reporting test results. So a standard score is a score that's expressed as a distance in standard deviation units between the raw score and the mean. There are several types of standard scores, and they include Z-scores, T-scores, SEB scores or CEEB scores, deviation IQs, and Stanine scores, just to name a few. And we'll go into each of these into a little bit more detail. But the idea, or sort of the umbrella concept of standard scores, is that you are taking a score and expressing it as a distance in standard deviations from the mean. So how many standard deviations someone's raw score is from the mean of that distribution, the average of that distribution. So let's go into a little bit more detail on Z-scores. A Z-score is the most basic of the standard scores. A Z-score distribution is a conversion that follows a normal curve, a normal standard bell curve, and the Z-score converts raw scores based on an assumed mean of 0 and a standard deviation of 1. So that means that a Z-score that falls one standard deviation above the mean is equal to 1, positive 1 Z-score. If you have a Z-score that falls one standard deviation below the mean, it is equal to a negative 1. A Z-score is calculated by subtracting the mean of a distribution from the raw score that someone has, and then dividing that by the standard deviation value of that distribution. So X is our raw score for the specific individual that we're looking at, M is our mean for the total distribution of everyone who participated in that assessment. And then SD is our standard deviation for that data distribution. If we plug in those numbers, we will get a z-score that is specific to that person. And it will tell us how far away from the mean they are in standard units, with 1 being the standard deviation. Because z-scores can produce both decimals and negative values, they can cause a lot of difficulties in computations and interpretation, so how to score them and how to understand them. And because of that confusion, other types of standard scores have been developed, and the most common of those standard scores is the t-score. A t-score distribution has a distribution mean of 50 and a standard deviation unit of 10. So one standard deviation is 10 units away from the mean. The t-scores can be more useful than z-scores in test interpretation because it does not have negative values. And a t-score distribution is calculated as 50 plus 10 times z, with z representing the z-score for that distribution or that observation. So t-score distributions usually range from about 20 to 80, and each range of the t-score is associated with different interpretations, as you can see on the far right column of this example. So the t-score is listed in this far left column, and that is again determined through this formula. 50 plus 10 times the z-score for the specific observation that we're looking at, which will then correspond to a specific interpretation of how they fall. So t-scores have been helpful, and they do provide a context for understanding things, but not all publishing companies or test publishers use t-scores as their standard score of measurement. And that's where we get our SEB scores. SEB scores are the College Entrance Examination Board scores, and a lot of college board scores are another type of standard score that's interpreted in the same way as Z and T scores, but they use a different scale. Specifically, SEB scores are used in ACT and SAT and other college entrance exams. SEB scores use a mean of 500 and a standard deviation of 100. And the formula to convert a z-score into a SEB score is exactly what we used for a t-score, just switching out the mean and standard deviation. It's 500 plus 100 times the z-score. This particular type of scale can cause a minor problem in that the small differences in raw scales may seem to be much larger because of the large scaled score differences that range from 200 to 800. So scores are all reported in increments of 10, and that's the formula that I already talked to you all about. But because there's such a wide spread, because we're talking about a mean of 500 with the most range falling within 200 to 800, what seems like a big difference in scores of saying like, oh, I got a 550 and someone else saying I got a 620, it seems like a big difference, but in reality, in the context of the distribution, that's not that far apart because the range is different. And that can cause some minor problems with the interpretation of these scores. And because of that confusion, some test publishers have moved into reporting the percentiles instead of the scores. So an example of this is if any of y'all had to take the GRE uses SEB scores, but they rely on the percentiles to explain their scores. Very few people actually know their real score on the GRE, but rather they know where they fell in their percentile of their scores. And we also have deviation IQ scores. And deviation IQ scores really came out of our very first intelligence tests, because when those first intelligence tests were developed, we talked about in week 1 that we had this ratio of mental age to chronological age, and how that ratio multiplied by 100 created the intelligence quotient. Unfortunately, the ratio for intelligence quotient or IQ had a number of problems, including the fact that the ratio for IQ became invalid beginning in the adolescent years. So, because there was this problem with the IQ using the mental age to chronological age ratio, we developed deviation IQ scores. And they're used with intelligence tests, and they have a mean of 100 and a standard deviation of about 15 to 16, depending on the test. So, this is the standard scores that are used in most, if not all, IQ tests. We'll talk more about IQ tests in week 3, but this will include like the Wechsler scales and the Stanford Binet now use the deviation IQ scores, which eliminates the ratio of mental age and chronological age and instead uses this assessment for determining your IQ based on this mean of 100 with a standard deviation of 15. And finally, we have Stanine scores. And Stanine scores are standard scores that divide a data distribution into 9 parts. So you have a standard normal distribution and you break it up into 9 different parts. And the mean of that distribution is then set at 5 with a standard deviation of 2. And Stanine scores are also in that image that I showed you before, image 6.4. So most Stanines, and we're going to go over image 6.4 here in a minute, but most Stanine scores are going to fall within 2 and 8, with the greatest percentage of scores as you move towards that 50th percentile of 5. So Stanine scores can be a little bit confusing because you're having to break up the distribution into 1 and 9, and only 4% of people are going to fall in Stanines 1 and 9, and the greater percentage falling between 2 and 8. So in our image that we've been referring back to, our Stanine scores are right here where you see the breakdown of someone's scores and where they would fall based on that normal distribution. I will be honest with you that Stanine scores are used incredibly infrequently because of the difficulty in explaining their meaning. A lot of people don't understand why Stanines 1 and 9 are so large, but yet only 2% of people fall in each category, and that the majority of people fall between 2 and 8, and like where they fall doesn't always make sense. So a lot of people don't use Stanine scores anymore. And then to wrap up our chapter 6 lecture here, I want to talk about standard error of measurement. So in chapter 5, we discussed reliability and the reliability estimate as the consistency of scores across a sample. The standard error of measurement allows us as counselors and assessors to evaluate an individual score within a distribution. So specifically, our standard error of measurement will tell us how much our theoretical distribution of an individual score is compared to a theoretical sample. If that sample were repeatedly tested with a large number of exactly equivalent forms of the same test. So in essence, if we can know a standard error of measurement, this allows us as assessors to construct a band around an individual's observed score to ascertain the range in which the individual's true score likely lies. So if you remember from chapter 5, we don't ever know someone's true score. We have their observed score on an assessment. And our standard error of measurement will say if we theoretically gave our participant the exact same assessment over and over again, equal forms of the same test, and they took it multiple times over, all of their assessment results, all of their raw scores would fall within a standard distribution, standard normal distribution, and based on that, we can say that their observed score is likely this close or this far away from their true score. So the standard error of measurement can be conceptualized as a standard deviation unit on a normal curve. So for example, if we constructed a confidence interval or a band of 1 standard error of measurement above and below an observed score, there would be about a 68% likelihood that our participant's true score would fall within that band. So that's how we use standard error of measurement, is how likely it is that someone's true score falls within one standard deviation of their observed score. So that is going to wrap up our lecture on chapter 6. And as always, here are some of the questions to help you understand this material and what it means in the context of our class. And I will see you all in the next lecture.